Okay, so let's start the lunch. We are happy to have Song on Zoom. Song will tell us about the correlators and amplitudes in N equals 4 super Young Mills, an invitation. So please, Song.
Thank you. I'd like to thank the organizers for the invitations. It's really a pity I couldn't get a visa to India to give this lecture in person. So I'll hopefully give you some overview of this topic. I'm sure you've heard from Paul on the this fascinating object called the half BPS correlators, and in it including the square of the amplitudes in this observable. And I'll actually base my talk on three aspects. So first, I like to talk about a method for getting the all loop integrands of the 4.5 BPS correlators, which are based on some essentially combinatorial and graphical idea, this well-known F graphs. And then I'll talk about how the same integrand could also be obtained from some geometric point of view, namely the Correlators that Paul has talked about. And within it, there will be the square of the Amplituhedron, which you can start from some geometry and compute a canonical form that gives you some rational algebraic expression for the integrand. And then in the last part, I will talk about some recent work on really trying to do this integrals or study some aspects of the integrated results of that appeared in this observable. So these are based on the works. In this paper, we've done the F-graph bootstrap with Canxin, Yichao, and Yaoqi. And then in this paper, we connect the amplitude square to energy correlator, which I'll briefly mention, and also study in this paper last week, we studied some loop integrations with Shihan and others. And also in this paper with Yuting and Jiakai, we studied the Correlators, a geometry related to Correlators. Okay, so please interrupt me if you have questions or comments. So I'll start with some very basic things that we know that amplitudes are given by n on-shell. The kinematics of the endpoint amplitudes are given by n on-shell momenta that you can draw as a polygon. And since it's in a planar limit that you'll study or given a color ordering, then you can also define these dual variables, the vertices of this polygon of the momenta. So the on-shell condition means that this is a light-like polygon, and momentum conservation means that it's closed. So from this dual points, you can also define the so-called momentum twister. So every dual point in twistor space will correspond to a line, or a pair of twisters. So how do we generalize here already at kinematic level to the correlators? So these are very important observables already, like 4-point ones. It depends on 4 generic points. There, you don't have any xij squared to 0. So this is or off depends on 4 off-shell points. That's the location of these 4 operators. That will study the simplest case, chase phi square. These are this 4-point correlator that depends on 2 cross ratios is a very important quantity that played a role for not only amplitudes but also ADS-CFT, conformal bootstrap, and so on. So unlike amplitudes, which is a cyclic, object that's cyclic in this x1 through xn, here is an object that's permutation symmetric in these 4 points. And as an integrated object, this is really, you can study it perturbatively by doing weak coupling. Weak coupling can do a perturbative expansion. But we'll focus on the loop integrands, actually. So for the loop integrands of the amplitudes, in addition to this on-shell light-like angle on for the external kinematics, you can also introduce the loop momentum. So the dual points for the loop momentum, y1 through yl for the L loop guy. So then the full amplitudes is given by the integration over all these loop punctures of an integrand. So this will be the focus of most part of the, I mean, at least the first half of the talk, which is the loop integrand that depends on external points and also this loop point. And it's actually already symmetric in all these loop points. You can make it. It's cyclic in the x1 through xn, but permutation in y1 through yl, right? So in addition to this intersecting lines that live in twistor space for the external kinematics, you additionally for the loop integrands, it also has L generic lines. Each line you can write as AB, again, a pair of twistors in twistor space. Okay, so this is the basic kinematics behind the Amplituhedron. So Amplituhedron is a geometry that lives in this external intersecting lines in a cyclic structure, and also this depends on L loop lines, which are permutation invariant. Okay, so now for correlator, it's even better. So the 4-point correlator can be written as a up to an overall prefactor. It can be written as an integration over L internal points that I already call x5 through x4 plus L. And then this integrand can be made totally symmetric in all these 4 plus L points. So we see there's no distinction for the loop. So for the loop integrand of the 4-point correlator, you don't have to distinguish between the external kinematics and loop points, essentially because this operator lives in the same multiplet as the Lagrangian, chiral Lagrangian insertion. So then you can really make this a Born level correlator that depends on all the 4 plus L points, and they are all symmetric. So in principle, now you can compute all this integrand for loop correlator that depends on all this 4 plus L generic points. It's permutation invariant, say by Feynman diagram. Okay, so actually that's what people did long ago. And it's, for example, if you want to compute 3-loop non-planar correlator, I think that's still the best method to done it by Feynman diagrams. And I want to mention that later we'll go to some limits that the external, you pick 4 of the 4 plus L points and take light-like limit in them to form a light-like foregone, and that contains you the 4-point L loop amplitude squared. And if you take a pentagon, light-like pentagon, it contains you, it gives you the 5-point amplitude squared at L minus 1 loop and so on. So this is the basic idea. So you once you know the loop integrand of the correlator that depends on all 4 plus L points, you can start to get amplitude squared out of it by taking various light-like limits. Okay. So there's a very nice graphical way to describe this loop integrand. So we want to find the rational function that's of the rational function that depends on all the xij square of these points. And since it's conformal invariant, so every point, every label, every external point should appear in this rational function with weight minus 4, because the integration measure is for d4L, right? And the external one, you just normalize it to have weight minus 4. So you can represent this graph, this rational function by a graph where you have 4 plus L denoted as n. So this n will be 4 plus L. And if you take really all the points to be light, it will give you n.3 amplitude squared. So this n is really, throughout the talk, it will be 4 plus L. So it will be a graph with 4 plus L vertices and with valency 4. Okay, so for each propagator with an xij square in the denominator, I draw a line. Then I will form some graph with 4 plus L points and weight 4, valency 4. Of course, I also impose planarity. Actually, at low level, like 1 and 2 loop level, you don't even need to impose planarity. These are the only 2 graphs you can draw with 5 points or 6 points, which has the correct weight valency 4 graph. Okay. So already at 1 and 2 loop, there's nothing to do. So just by knowing that the thing should be symmetric in 4 plus L points. So remember, when I draw these graphs, I never label who is 1, 2, 3, 4, 5. I mean, this graph represents a permutation sum of all possible labels. So this term is just the product of all xij square. It's a complete graph for 5 points. And this 6-point graph, if you write down the rational expression, it's really a sum over all permutation of the 6 points, where each term appear with coefficient 1. So there's this symmetry factor in front. So remember, at 4, 5, and 6 points, which are 1 and 2 loops, there's a single graph, a single F graph. So that gives you the loop integrand, because that's the only rational function that can have conformal weight, a correct conformal weight, and also permutation invariant. So starting 3 loops, starting 7 points, this is no longer true. So you can have many graphs, but when we consider planar limit, like the number of color goes to infinity, again, at 3 loops, actually, there's a unique graph. So this graph now start to have a numerator. So at 1 and 2 loops, you just draw this weight 4 graphs. Every point has valency 4, right? Give you the correct weight. So at 7 points, you start to have 2 vertices that has valency 5. So you need a numerator to cancel to give you the correct weight. Okay. So
can I ask you a question?
Yes. Go ahead.
So when I look at the graph, what tells you that it's a 1 loop graph or a 2 loop graph or a 3 loop graph?
Yeah. So the best way to understand this is that this is the graph that gives you. So you should really not look at the loop of this graph. You should really look at how many vertices are here. So this is really a graph that gives you the Born level result for 4 plus L operators, where 4 are the external four operators, and the L of them are the Lagrangian insertion. So when you look at a 6-point graph, you're really looking at a 4-point correlator with 2 loop insertions. So this describes you 2 loop. Okay. So really, when we look at the n-point F graph, it describes you n-4 loop correlator, the integrand of the n-4 loop and 4-point correlator. Is that clear?
Yeah.
Great. Any other questions? Okay. So at 3 loop or 7 points, so you should really look at it as some Born level correlator with 7 insertion points. Again, if you require planarity, then there's a single graph. So this single graph represents such a permutation sum of all this solid line with denominator, and this dashed line is numerator. So I also I think it's from Paul's paper that if you draw these two dots with some color, it denotes some numerator is needed for this. Okay. So here comes the bootstrap question, right? So any n-point F graph, remember this describes you some 4-point correlator with the integrand of 4-point correlator with n-4 loop insertions. It's just a linear combination of this F graphs with some number. These are just some coefficients. So the question becomes how to determine these coefficients. I mean, at 1, 2, 3 loops, it's just the overall coefficient that can be fixed to be 1. But at starting 4 points, there's something interesting. So actually, you can generate all these F graphs. So if you don't care about planarity, it's this number. We've done it up to 10 points. But then if you consider planar F graphs, or you can also consider more detail with plane embedding. So there are slightly more plane embedding F graphs than planar F graphs, because some F graphs at very high points, starting 12 points, has different plane embedding. But anyway, you can easily, using plane tree, list all these graphs which has valency at least 4, and including their numerator structures. So this number, of course, increases very fast. When you get to like 16 points, it's more than 6 times 10 to the 8th, I think. Okay. So the job, the bootstrap, the task of bootstrap is to determine all these coefficients for the planar F graphs. And this has been done very beautifully less than 10 years ago by Jake, Paul, and the collaborators. They use various constraints from physics to bootstrap these 210 loops. So 14 points, up to 14 points, using a series of rules from how this graph should reduce back to amplitude square, all these consistency conditions when you reduce it to, say, 4-point amplitude square or 5-point amplitude square. It gives you enough constraint to fix it. For example, there's the so-called square rule that's very similar to the amplitude run rule, which says that if you have this structure of a square, if you remove it, if you have a square and another loop points inside it with this structure, like pyramid structure, then if you remove this point, you should connect your n plus 1 point graph to n point graph. So their coefficient should be equal whenever you see this graph, this kind of structure. Okay, so this comes from a constraint that you ask the correlator to reduce to 4-point amplitude squared consistently, and it's actually already very powerful in fixing coefficients. It's the percentage of the coefficient fixed by this square rule. Of course, when you go to rather high loops, still huge numbers of graphs cannot be fixed in this way. So they don't have this square structure. So there are also pentagon rules and so-called triangle rules from OPE. So I'm just showing you some example. Like at 4 point, there are 3 F graphs with coefficient 1, 1, minus 1. So this last one has no numerator. It's a very nice graph of, it's actually a graph of 5 to the 4, right? It's all valency 4. And the first 2 graphs has numerator. And at 5 loops or 9 points, you have 7 graphs, and their coefficients are still plus or minus 1. So these are classic results from long ago, and Jake and Paul and collaborators, they managed to do it up to 10 loops. So next I'm going to describe you very quickly a new rule which allow us to actually fix this, push this frontier 2 more loops. So we did it in the last October up to 11 loops, and recently we did it to 12 loops. And the computation complexity, every loop order, it increased at least like 20 times. So that's about the limit we can reach at the point. But I think the message here I want to say is that there is a very beautiful new rule from this so-called cusp limit, which we don't need any other rules. It's just a single universal rule by taking 2 like limits of your correlator that allow you to fix all the coefficients. Okay, so I don't want to go to too much detail for this rule, since this is just the beginning of this story. But I just want to remind you that in the early days, people proved that the Lie-like limit of the correlator equals the Wilson loop in the adjoint representation. They take this Angon Lie-like limit. So here we're taking something much simpler, but the argument from the physics is exactly the same. So we only take like 2 Lie-like limit. We have many insertion. We have many points, but we take 1, 2 square to 0 and 2, 3 square to 0. And in this Lie-like limit, you find that the leading contribution is coming from another point pinching with this cusp. Okay, so this is why we call it the pinching rule. So translating to the rational function, it looks like that. Remember, this is something you can only done in the Lorentzian signature, that you have to take this 2 Lie-like limit. But by using the same argument as the proof of duality to the Wilson loop, you show that the leading divergence of this is given by a 1 loop diagram, where you just have the Sudakov double log from this pinching. And that gives you a very nice rule. It says that when you look at the n plus 1 point graph, whenever you see such a structure, you take the pinching of these 2 points. It has to reduce to a cusp diagram at 1 point lower. So it relates all these coefficients of a n plus 1 point guy to a single n point guy. Okay, and since this double triangle structure is everywhere, and this cusp structure is literally present in every graph of n.1. So this rule is giving you very, very strong constraint, essentially constraining every graph in all the coefficients in the story. So here is just a very simple example. The first really non-trivial example, you look at your 8-point guy with 3 F graphs, and you just start to looking for this double triangle structure, and then you pinch the double triangle into a cusp. So whenever you pinch it to a cusp, you reach at the low graph with 1 point lower. But sometimes you directly get to a non-planar graph. Since we're working in a planar limit, this graph has coefficient 0. This non-planar graph has coefficient 0, right? So you immediately get a lot of constraint, like the pinching of this graph can only reach here. So remember, at 7 points, there's only 1 graph. This is the only planar graph. So you see that the coefficient of this guy must equal to the only coefficient of the 7.1, I call B1, and the coefficient of this one also equals B1. But then there's this way of pinching that reach you to the non-planar graph, same from the third graph. So it tells you that the second and the third graph has to add up to 0. Okay, that's the third equation you get. So from these three equations, you can fix, you can solve all the n+1 point coefficient in terms of the n.1. The n.1 has only 1. Okay. So in this way, you can really, so we just run this bootstrap, and without any other input, you can fix up to 11 loops. Except one small caveat is that indeed there are very few exceptional graphs that don't have any double triangle. So these graphs are very exceptional. At 12 point there's 1, 15 point there's 1, nothing in between, and 16 point there are 2. So these graphs don't have any double triangle. So immediately they are called invisible F graphs. So immediately you will see, oh, they won't be detected. But it doesn't matter, because this equation that go from n+1 point to n point, when it at the same time fixing all the n+1 point ones except the invisible one, it also fixes all the n point one. So all you need to do is to go one loop higher. The invisible ones will also be fixed, because it can be obtained by pinching of another guy. Okay, so in this way we fix all the coefficients. Here are some statistics. You can see that the majority of them are 0, right? So that's the like when you go to 11 point, 90% of the coefficients are 0. But you start to starting 12 point, you start to see some very interesting numbers. I mean, already at 10 points there's a 1, 12 point there's a 2, there's a plus or minus 2, and then at the 12 point there's a 5, and the 14 point there's a 14, and so on. And you also there's a unique there's a single unique largest coefficient, like -1, 2, -5, and 14 at each even points. And there's also the smallest unit that at 12 points you start to see a half, at 14 points you start to see a quarter. And very recently, just last month, we managed to do it for 12 loops. So the highest record now is 16 points, together with Jake and Tanxin and Yichao. So this is really a huge computation involving like this number of F graphs. In the end, it give you like 95% of them coefficients are 0, and we can see more. The unique large coefficient now turns out to be -42. Okay, and there's also other distribution of the coefficient that I'm not gonna talk too much here, but just want to remind you that the most coefficients are 0, and also they are accumulated at things very close to 0. So these large coefficients like 42 or 14 and so on are very rare. Okay, so this is a number of distinct coefficients increase as the number of loops. So at 12 loops you see 70 distinct coefficients with the smallest interval 1/8, and but most of them are accumulated between like -2 and +2, or -5 and +5. Only very few are jumping to 14 and exactly a single one to -42. Okay, so that's really a very beautiful problem of how all the coefficients are distributed and what's the statistics and so on. But I just want to point out this special graph. So what's this special graph that has the largest coefficient at each even point? This is called the anti-prism. Okay, so at this 2m points, you can have m gone on the outside and the m gone on the inside, and then connecting them by this small triangle. So this is a 6-point guy, this is an 8-point guy, and 10-point and 12-point, and so on. So this is what we call an anti-prism. This is the graph that has the unique largest coefficient. So -1, 2, -5, 14, and so on. So in our last paper, it's very embarrassing that we were unable to do all the 16-point calculation, but we found a trick to just compute the coefficient of this one by something called a local system. But then we made a mistake in that calculation. We thought, okay, this so-called Catalan conjectures breaks down at this 12 loops because we find -38. Now, after correcting that bug, it turns out to be minus 42. So in my talk like last November, I talked about why I mean the Catalan conjecture breaks down, but it's actually it actually still holds. I want to take this opportunity to correct this. So it's in the new version of our paper. And now since we already computed all the 12 loop thing, okay, the 12 loop thing is completely solved. So we don't rely on this local system. It's completely confirmed that the 16-point antiprism has coefficient minus 42. So I want to say that this antiprism has a very beautiful interpretation in a tree-level squared story. So remember, the F graph can be, I'll talk about this later, but if you take like a n-gon limit, we involving all the points, like really connecting every point in this find the n cycle that connects every point in this antiprism. In the F graph, you do get some tree level amplitude squared by summing over all the super multiplied in the external state. So this antiprism has the special status that it contributes to the constant piece in the tree level amplitude square if you divide everything by the MHV square. Okay. So remember, if I take n-gon limit of my F graph, I get tree amplitude square. This tree amplitude square is the summing over all k sector, like MHV square, next MHV square, n square MHV square, and so on. And it's a very nice function of all this xij square. But in it, there's a constant piece. The constant piece only receive it can only be obtained from the n-gon limit of the antiprism graph. So this Catalan number is telling you what's the constant piece of the tree amplitude squared. So now we can confirm that the 16-point squared is minus 42. You may ask, why do we have to compute all the very high loop F graph to get something about tree amplitude? The thing is that the tree amplitude squared is something very hard to compute or to simplify. If you take, say, BCFW form, I'll talk about it very soon. If you take up like BCFW form and square it, it's very hard to simplify into a local form and then extract the constant piece. So far, I think this 12-point square and 14-point squares are completely out of the question. No one knows how to compute the chi square to confirm this point. Of course, we know it from the F graph result that if you were able to do, say, 16-point chi squared, the constant piece will look like minus 42 now. Okay, so that's just something I want to report about really the combinatorics of all these graphs contributing to the correlator and also amplitude square. And there's one more thing that we found very, very recently, that the antiprism can be even generalized to some, there's a common generalization of so-called fishnet graphs and antiprism graphs. So if your antiprism graphs start with this foregone case, okay, the m equals 4 case, and you start to weave in this diagonals. So this is your antiprism, and you start to like weave in some diagonals, increasing the loop order. You can weave in more diagonals. You can do this and so on. This is literally the so-called Basel-Dixon fishnet graph. Okay, so if you take the outer foregone limit, it becomes a 4-point conformal integral that's in the Basel-Dixon fishnet. And we know that their coefficient in the correlator come with plus or minus 1. Now we have a generalization. So if you have a pentagon type of antiprism and start to weave in things, you start to see some fishnet within the pentagon antiprism and hexagon and the heptagon and so on. So these are all this what we call antiprism net or polygon fishnet that up to 16 point that we computed. So look at their coefficients. Their coefficient certainly exhibits a generalized Catalan conjecture. Okay, so what's this conjecture? This conjecture is saying that for this type of graph, you only need to take all the inner faces, look at what gong you get as the inner faces, and for every k gong, you take a signed Catalan number of k minus 3. So for every triangle, you have 1. For every square, you have minus 1. For every pentagon, you have plus 2. For every hexagon, you have minus 5. And for every heptagon, you have 14, and so on. So the original antiprism, of course, only has one non-trivial K-GAW, right? All other things are triangle. I'm not taking the contribution from the outer face. It's just the inner faces. Okay, so that's the Catalan conjecture. Now we are generalizing it. So all these things have the product of Catalan. So for example, why this graph has -2 because there's a 2, there's a -1. Why this graph has +5 because there's a -5 and -1. And more interestingly, there's this graph with 2 pentagons that has coefficient 4. So it's 2 times 2. Okay, this is 2 times 2 times -1 with a 2 pentagon and a square. And this is -14. And this is actually -10. There's a hexagon with -5 and there's a pentagon with 2. So this is a very beautiful conjecture that we now say that not only the original antiprism, but they are common generalization with fishnet. We conjecture them to have this coefficient. And I'll give you some exercise. So these are some interesting examples appearing at 18 points. So you can tell me later what are the coefficients of these guys just by the rule I just told you. And there could well be that these stories, I mean, this integral, just like the original fishnet, could be very interesting finite integrals of higher points. And maybe there are some other integral model associated with that we have no idea. So far, we're just saying that their contribution to the 4-point correlator integrand is very special. They have this product of Catalan as their coefficients. And there's might be even more generalization. So these graphs are still very special. We really considering like weaving in this fishnet inside the antiprism. But you could ask, could it be the case that for every graph, the result is the coefficient is given by products of this? That's certainly not true because there are some half and the quarter and so on. But maybe there's a generalization of the rule to really tell you graphically what are the coefficients and how to prove this rule. I mean, so far, it's a conjecture, but if we can really solve the local system recursively, there's a way that maybe we can prove this rule. And as I also mentioned, that this coefficient contribute to tree-level square, and it also contribute to all this 4-point loop integrands or 5-point loop integrands and so on. So there must be an interplay between all this Catalan number with the requirement that you should have unit leading singularity in the lie-like limit. Okay, so these are all interesting data that one can play with for the correlator. So that's the first part I want to tell you, that there's this bootstrap for F graph with very interesting coefficients and a very interesting new type of graphs. So any questions so far?
Yeah, question. Actually, I have 2 questions. So okay. Are you still using this lie-like limit as the only constraint?
Yes.
Or
yes.
That's the only constraint that you are using, nothing else?
Exactly, yeah.
Okay.
So except for the invisible graphs which you have 2 here. At 16 points, you have 2 invisible graphs. So for them, you need something else. But we know that if you could go to 17 points, then this 2 will also be fixed by our rule. It's just 17 points takes too long to compute. Yeah.
Mm-hmm. And so, this rule with the Catalan numbers, do they explain all integer coefficients, or are there some integer which are not?
No. It's very sparse. The large coefficients are very rare. You can look at this table. So anything between 14 and anything with absolute value larger than 14 does not exist, except this -42. So, at this loop order, I mean. So all the coefficients are tend to concentrate on very small numbers, like between -1 and 1, or -2 and 2, as the loop order increases. But the -5 or 14 or -42, those are very exceptional ones, and maybe you need to wait until 20 points to see that -42 and +42 are filled in. Yeah. So it's like every loop order or every 2 loop order, you have a new hierarchy. Like you go to a very high next Catalan, but between this Catalan and last Catalan, there's a desert. There's no particle between them. Completely empty. Yeah.
Also, your comment about leading singularities, we know that for the amplitude in the lie-like limit, we don't have just unit leading singularities.
Okay, yeah.
Right?
Sorry.
These numbers, do you think, are these numbers related to your numbers or not?
I don't know. So that's related to a comment Jake made, that the original antiprism, if you look at them as 4-point contribution to the 4-point integrand, they may be tuned to cancel many other contributions to give you unileading singularities. But in general, I agree that that's not even true. So we have no idea how this Catalan number play with the coefficients of the amplitude story. I mean, I think the simplest way to see them is really in the tree-level squared. So if we have the analytic control of all the tree-level amplitude squared and take some limit to get rid of all non-constant p's, then there's a way to extract this Catalan number directly from tree-level squared. But right now, I think we cannot do it. So if you take all the BCFW expression and squaring them, and then taking some limit, I mean, already at 10 point, it's computationally too challenge to do it. Yeah. So 10 point, you expect a 2. I guess that 2 you can extract, but then 12 or 14 point or higher, we don't understand how to extract how to confirm this from literally squaring the tree. Yeah, I think that's the that should be the easiest way to see, because you don't need any higher loop data. But so far, even the tree level square is a difficult problem.
Okay, more questions?
Is it clear why there is this alternating minus sign in the Catalan conjecture?
Good. So yeah, I think from the equation, it's kind of clear that you need lower Catalan numbers to have like okay. So already you can ask why this is -1, right? This is actually the first appearance of -1 instead of the at even lower loop it's just a +1. So this is the first -1. If you look at the equation, you see that they cannot all be positive numbers. So there's something add up to 0 and so on. So if we want to prove this conjecture that at the highest loop level, this antiprism itself is given by some sum of lower product, we do need all these alternating signs. Yeah. But we still don't know how to prove it. I mean, that's just still a wishful thinking. I mean, we of course our equations explains why this is 2, this is -5, and so on. But we don't have an all loop explanation of the alternating sign. I think that's part of the proof that if we can really recursively show that this graph has this coefficients. Yeah.
Okay. No more questions. So yeah, please continue.
Okay, great. Let me move to the second part, or maybe I should tell you the answer. This is 25. This is 8. This is 132. It's just the product of Catalan. Very simple things. Yeah. So the second part, I want to talk about some Lie-like limit of these things. Okay. Also including itself, but I think the Lie-like limit is the most interesting thing already. Like if you take the foregone, if you pick any 4 points and take the take this Lie-like limit of the foregone Lie-like limit multiplied by this prefactor, you get the 4-point amplitude at L loop squared. Squared here literally mean that you have all the lower loop products that add up to L, right? So actually you can pick that when you take the foregone, if it contains L prime points in one side and L minus L plus point on the other side, this is a particular contribution. So for 4-point amplitude, there's really no need to say that it's amplitude squared. So if you take all the foregone that contains 0 points inside and all the points are outside, you literally get a single contribution, which is the 4-point L loop amplitude. Okay, so for 4-point amplitude, you can the 4-point amplitude or 4-point amplitude to any loop order is contained in this object. So for example, you take that 5-point graph and do a foregone limit, you see literally this box integral. And the 6-point graph, there are 2 ways of taking the foregone limit. I leave this as an exercise. You see either a double, the dual graph of a double box or box square with the same coefficient. So these are how you obtain 1 loop and 2 loop squared, 2 loop 4-point amplitude. No square. Here it's squared, but they are actually separated. So if you take the way the foregone limit without anything in between, you get exactly this term, not the second term. Okay, so all these products can be extracted from different foregone limits. And now I want to talk about something even further, that you can actually take pentagon or hexagon like limit, which give you now amplitude square. This amplitude square is actually has to be a square. You cannot distinguish. I mean, you can still distinguish different L prime contributions, but since there's also a squaring in the k sector, so you're taking some nk MHV amplitude and squaring it, gluing it with the parity conjugate. Okay, so starting 5 point, you already have the MHV times MHV bar. 5 point is still relatively trivial, but for 6 point, you have the MHV times MHV bar, but also next to MHV squared. You need so the F graph can never distinguish you between different k sectors. It always give you a sum over all the k sectors. So for larger than 4 point. Okay. So I want to take a very special limit I already mentioned in the first part, that if I take all the endpoints and in an angle like limit, then I get the chi squared. There's no loop, so there's no summing over L prime. Here is just a summing over k. So this is literally the cross section of the chi amplitude, but I also divided it by the MHV mod square. So this gives you a nice conformal invariant function with simple posing this xij square. I think this is a very interesting function to study. I mean, you can also do it from the BCFW. Any expression you have for chi amplitude, you glue them together and sum it over all k. But it's very difficult to simplify them into this local form. They're all spurious poles and so on. So let's take an example. The 6 point square, the chi level 6 point square. How does it look like? There are two ways of taking a 6-gon limit of this graph. One of them give you 1. This is literally the MHV square, because I divided by MHV square. The other give you this cross ratio, a three cyclic image of this 2415 over 2514. I mean, this bracket is just xij squared. So this 3 term is actually the 6 point next to HV squared. It's a very nice result that 6 point next to HV squared give you these 3 cross ratios. And for 7 point, you start to see more interesting cross ratios. I mean, they are the 7 point next to HV squared and so on. So what I mean before is that if you compute the whole chi level squared and find some limit to send all this cross ratio to 0 and leave with only the constant piece, that constant piece has to be Catalan number, alternating sign Catalan number at every odd point, even point, because at odd points there's no constant piece. At all points, everything you cannot build a constant piece out of the odd angle. But for every even point, there's a constant piece, and that constant piece is exactly the contribution from antiprism in this angle limit. Okay. So of course, there are some other physical application of this chi amplitude square called the splitting function. They serve as the integrand of energy correlators. So if you parameterize your xij squared in terms of some collinear particles with energy detectors, with some energy fraction and some angles, then this ratio, this chi level amplitude squared divided by MHV squared is exactly the integrand in this collinear limit, is exactly the integrand for the endpoint energy correlator. So that's why people are also interested in this local function of xij squared. If you take the collinear limit, they give you the integrand. And it's of course given from, you can extract it from F graph to very, very high points. But at the same time, it's also computed by the geometry. So before I go to geometry, let me show you the 6-point example. It's a very interesting calculation, I think, found in also in Paul's paper. So the MHV bar amplitude is this top form of G26 or G46. But then the next MHV amplitude looks like that, right? So you need to square this guy, okay? So when you square this guy, every diagonal term like this R invariant squared give you 0. But you have these cross terms. These cross terms divided by the top form give you some cross ratio. So this is the origin of this cross ratio. So you see that the 6 point next to HV squared divided by the top form is exactly given by this cross ratio plus cyclic. So you can also compute from BCFW, but starting higher and higher points, this BCFW form has more and more spurious poles, and it's very difficult to simplify them to the local form. So far, all the data we get at higher points are from the F graphs. But I want to really make the connection that I don't think people have really explored this connection, which is all these nice functions of cross ratios multiplied by the top form is nothing but the canonical form of the tree Amplituhedron squared. So in principle, this should be the best way of computing them. So you just start with this definition in this paper is that the tree Amplituhedron squared is something, after you summing over all the k sector, is actually something much simpler than individual Amplituhedron, right? At each k sector. So there's no sign flip, and you just if you find a nice way of computing the canonical form, but there's some issue with this weighted positive geometry. But anyway, if you find a way to compute the form of this simple geometry, you should reproduce all these nice local functions, and in particular, you should see the Catalan number out of this geometry. So this is something we I think nobody has been able to compute the form of the geometry beyond, say, 7 points or 8 points. That's the highest that you go. And remember, when you literally compute the form before simplification, it doesn't look at anything local, right? It looks like BCFW form or something like that, some triangulation of the geometry. And just at 6 and 7 point, you observe that every term in the triangulation of this geometry is given by some product of x coordinates. Okay, so this explains that this amplitude square at each k sector is already manifestly positive because in a positive region, because it's positive combination of x coordinates, which is not clear from the local form, because you see my Catalan number has all these alternating signs and so on. So if you write it as a local form, there are terms with plus and minus signs everywhere. But if you derive it from geometry, as anything from this geometry, you know that it should be positive. I mean, we explicitly check that in this geometric way of computing them, you see them as product of x coordinates. Even for each k sector, is already a positive thing at each k sector. Okay. So this geometry is, of course, can be generalized to the Correlators, which I think I will talk only very briefly because I think Paul already talked about this original Correlators geometry and also this equivalent way of formulating the geometry for the 4-point L loop 4-point L loop integrand of the correlator that Jaka and Yuting I work out with them. So there's this way of viewing all the loop geometry as a fibration of the tree kinematics. So for every point in the tree kinematic region, you compute the loop form. But then when you vary from one point to another point, the loop form can vary. So this gives you the idea of chambers. Okay. So I don't want to go into details of this geometry because I think Paul already talked about it. But remember, the geometry only exists in the domain that delta square is positive. So you compute the tree form with this boundary that has this local xi dot xj, but also the delta as a boundary. So this is your tree form, and all we are providing is a chamber, a way based on these chambers to compute all the loop form. Okay, so for all the loop for every point in your tree region, you can compute some loop form, but then depending on different loop form you get, it dissects the tree region into different chambers. So eventually the canonical form that you compute is given by some product of the tree form times the loop form, summing over different chambers. So at actually 1 and 2 loops, there's no chamber. So you just compute the loop form is uniform across the whole domain. So you can just directly compute the loop form for 1 and 2 loop given by, say, 2 loop given by the double box and box square, again from the not from the geometry. But now 3 loop is very interesting. 3 loop, you start to see some appearance of different chambers. And by the way, this chamber idea is also useful, a powerful method when you want to compute higher loop and higher point Amplituhedron, canonical form for the Amplituhedron, because now you can, based on the chambers given by intersection of BCFW regions, you can compute the loop form for each chamber also in the Amplituhedron case. But for the correlator, say we did it for 3 and 4 loops, and the 4 loops has not been published, but the 3 loop is very simple, that you have 6 chambers. So each chamber has its own tree form, which is like a prefactor. So this chamber also tells you what could be the prefactor of your answer, right? So within each chamber, you compute the loop form. It has to be given by some union leading singularity thing. So we expect it to integrate to some pure function. But then each tree form for each chamber give you the prefactor. So this is really predicting that at 3 and 4 loops, you have 6 prefactors given by each tree form of the chamber. And for 3 loop, of course, you start to see this tennis court ladder easy hard integral appearing from the form of the geometry. So at 4 loops, you still see these 6 chambers, but now you also see an elliptic cut. So that's a very interesting observation, that you do see 6 prefactors multiplied by some loop form, but there's a piece that loop form cannot cut to the end. There's really this elliptic cut that tells you that starting 4 loop correlator, you start to see some expect some elliptic function. But anyway, I think the Correlators is still at a very early stage. I mean, the way we study the loop geometry for correlation. For one thing, the way we can compute all this loop form as a fibration over tree form is really by breaking the symmetry, right? We have to pick 4 points as our base, and then the remaining L points we compute the loop form. Unlike the original definition of Correlators, that should be really symmetric for all the 4 plus L points. But we don't know how to compute canonical forms based on that definition. So in order to compute anything, we break the symmetry. So I think it's still a very important question how to recover the symmetry, like really compute the thing, and also how to extract all these squared amplitudes out of this geometry. That will provide a lot of simplification. So this geometry itself is very complicated, but when you start to take like limit of the geometry, that should be much easier to study. Okay, so any question for this part of the Correlators and the Amplituhedron squared in the like limit?
Don't see any, so you can.
Okay. So I'll move to the last part. I mean, I guess I'll leave more time for questions in the end. So the last part, I really want to describe you some new progress that we've achieved in computing the performing the loop integrations for these things. So of course, what do we get here is that we have a function, rational function that depends on 4 plus L point, and after you're performing all the loop integrations, you're left with the 4-point correlator, which is really a function of 2 cross ratios. And these loop integrations are very hard to compute already at 3 loops. I mean, it's very difficult. But in this paper in 2013, the authors they managed to bootstrap all the integrals at 3 loops, including this so-called easy integral, hard integral, and so on. So I think it's a very, very important question of what are the functions and how to bootstrap them at even higher loop points. So even higher loops. So as I mentioned, at 4 loop, there start to appear elliptic function, but most of the integrals are still multi-polylog. So actually, you can set up a single-valued multi-polylog bootstrap. I mean, I won't go into any detail about these functions, but for the experts in the audience, these are some generalized polylogs of uniform transcendentality weight 2L, but they have very simple alphabet. So for most of these integrals, they only depend on 4 letters: this z bar and 1 minus z bar. So these integrals are known as the single value harmonic polylogs. And then with more complicated integrals, you can see a 5th letter, like some z minus z bar, or sometimes you see 1 minus z bar. So the function space, whether it's single value harmonic polylog or a slight generalization of it, is very easy to construct. So the difficult thing is in order to bootstrap the whole thing is what are the prefactors, what are the leading singularity? But now we know them from the geometry, right? So that's why we can move to even higher loops. And I think there's many interesting results here for the integrated things. For example, there's all loop results from integrability. I mean, first there's the ladder integral that's known to all loops, but there's also this fishnet integrals that I already mentioned. I told you this is the starting point of all generalized the Catalan conjecture. They only have plus or minus one coefficient. But thanks to integrability of first to Basil-Dixon, the integrability result from this paper, that all these fishnet integrals are given by some determinant of this ladder integrals. So then in a recent paper of Simon and Frank, that they use this 10D symmetry to even generalize further and compute all so-called all these Coulomb branch amplitude, which are obtained by taking 10D Lilac limit of the correlator. And very nicely, all this Coulomb branch amplitude in this definition are known from integrability, from the so-called octagon, the large R charge correlators, completely known again as determinant of ladders. So that gives you an opportunity that you can study all these integrals, and when they combine to some Coulomb branch amplitude, their results are known. Their results are given by determinant of ladders. So we want to explore how we can get more constraints on the integrands and on the integrals from this Coulomb branch amplitude equals octagon result. Right. So the Coulomb branch amplitude really has an expansion in this R charge of the 6D part, right? The 10D distance is given by the 4D distance and with this R charge part, and it has an expansion in this power of the 1 minus D13 or 1 minus D24 called MAB. And since all these results for MAB are known from this octagon result, so now we have an opportunity that the MAB is given by some F graphs. Each MAB can be extracted from some F graphs. And the result for after integration of these F graphs are known. So at least this combination of F graphs should their conformal integrals evaluate to something well known. Okay. So for example, you can already study at L loop when L equals this A times B. There's a unique graph called the fishnet graph. So from your F graph point of view, you see more graphs, but there's a unique fishnet graph that equals the correct result. So that tells you at this order, if you see anything beyond this fishnet graph in your F graph bootstrap, they are all zero. Okay. And I want to emphasize that this way of constraining conformal integrals from the octagon result does not apply to all integrals. They only apply to the integrals that contribute to Coulomb branch amplitude. For example, at 3 loops, all this easy and hard integral, you cannot see them in the Lilac limit, right? So these are really only tells you all those conformal integrals that contribute to 4-point amplitude, not 4-point correlate. So our ultimate goal is want to compute all the conformal integrals contributing to 4-point correlators. But if you want to use the result from octagon, they only tells you those DCI integrals that contribute to amplitudes. So for 3 loop, there are 2 of them, the ladder and the tennis court. And there's very beautiful metric identity, so-called metric identity satisfied by this integral. So already at 2 loop, you know the double box has this identity. So it tells you that the ladder, 3 loop ladder and the 3 loop tennis court is equal to each other. And this tells you many higher loop things are all equal to ladder integrals. I mean, they are consistent with the Coulomb branch result. So by extracting more and more Coulomb branch amplitude from octagon result, you can list more and you can enumerate more and more such metric identity as higher loops. I mean, these are simple metric identity which basically follow from a 2 loop metric identity. The implication of this 2 loop metric identity. But now you already see that at 4 loop, there's this new metric identity which is telling you the fishnet equals the combination of this other 2 guys called D2 and F. So if you this integral is called D2 in the literature, and this integral is called F. If you take the linear combination of them, they give you the fishnet. So this is the consequence of the octagon. Of course, individually, these integrals are not known. I mean, perhaps except for the fishnet, these integrals are known. But you know the combination. They have to add up to 0. And you can use this again to generate more and more new metric identity at higher loops. And by octagon result, you can subtract those simple magic identity from lower loops and obtain new, really new magic identity at 5 loops or 6 loops. So these are all linear relations of this conformal integrals that nobody knows how to explain from primary integral point of view. But integrability tells you that their combination has to be 0. Okay, so this is one thing I want to talk about, which is you can generate many identities, but still you see that you cannot compute individual integrals. Okay, so at higher loops, even for the dual conformal integral contributing to amplitudes, you only know the final result when they combine to the amplitudes, which are determinant of ladders, but you don't know them individually. So we go back to the bootstrap method, right? So as I already told you, these DCI integrals are much easier than the general conformal integral. So we can compute their leading singularities easily, also from the geometry, but also you can also directly compute their leading singularities. And then you can also list the alpha bit, which are or the for the single value harmonic polylog, it's like that. And then there's generalization to more general cases. So up to 4 loops, they are all given by a harmonic polylog, and starting 5 loops, you see new things. And then you can also have constraint from metric identity or from other boundary values and so on. So let me show you one concrete example of the 4-point case. So here you have this. This is the D2 integral. This is the fishnet is called the F2 integral, and then this is the most difficult one is called the F integral. We know they satisfy a metric identity. Of course, the fishnet is known from integrability, but let's pretend we don't know them. So we need to list the ansatz for them. So you compute the leading singularity of D2 integral is 1 over delta. The leading singularity for F2 integral is 1 over delta square. And then you list their the function space is this is a parity odd single value harmonic polylog, or this parity even one. And you impose some boundary value, or you impose some differential equation. Immediately you can fix this function very easily. So the D2 and F2 integral take very simple form of this harmonic polylog. And the F integral is slightly more complicated, but still, since it's given at least the linear combination is known, so you can also bootstrap it. So the leading singularities are given by 2 pieces. One is delta, the other is delta square, but with this prefactor. And now you again list the coefficient and impose these boundary values. You get this result. So this can be viewed as an independent check of this magic identity, which before you only know from integrability. Now you can really bootstrap all these 4 loop DCI integrals individually. Okay, so you may wonder, since they combine to amplitudes is already known in the Coulomb branch amplitude, why do you bother to compute them individually? Because once you know individual integrals, they may give you other quantities you want. So if you expand other quantities into these integrals, now you can use this result. And we also did some 5 loop bootstrap, but there are some complications start to arise, because there are some F graphs in 5 loop case that do not give you uniform transcendental things. So you need to take some combination, I think. So 5 loop is the first case that you see some DCI integrals that evaluate to lower weight pieces like this. There are 34 DCI integrals, and there are 34 DCI integrals, and the 33rd one give you a purely weight 9 contribution. And then there's also some other integral that give you weight 10 plus weight 9. So you can already see them from the leading singularity. So the leading singularity tells you it can be used to give you the maximal weight piece, but there are pieces that you cannot compute the leading singularity like this integral. So it actually has only a weight 9 piece. Okay, so this is the last thing I want to mention is that you can also compute just numbers out of this. Now these are all conformal functions of u and v out of the each DCI integral. But if you look at the F graph without specifying which DCI integral you go to, if you integrate over all points, all the 4 plus L points, you get a number. This is called the periods of that graph. And there's a lot of study of these periods in terms of these multi-zeta values related to the integrated correlator and so on. So there are also constraining from integrated correlator like localization or integrability. So I think it's a very beautiful question that now you can ask at even higher loops. What are the periods of this F graphs? In particular, what are the periods of this determinant ladder? The graphs correspond to determinant ladder. Since we start to see some periods are not uniform transcendental, but you need to take more combinations to recover the UT property. So this will be a even simpler object to study, which are the periods, not the conformal functions. Okay, actually, I think I have plenty of time. I'll just end here and mention some open questions. For example, this graphical rule for all loops actually also apply to non-planar F graphs. But now for non-planar F graphs, it's already not enough at 4 loops. It does not fix all the coefficient at 4 loops, and so you need more things to do if you want to compute the non-planar correlator integrands. And of course, I mentioned the combinatorics of the F graph, like the generalized Catalan, and how do you understand all these coefficients and their relation to the tree-level amplitude square. I think already there's an interesting question: how do tree-level amplitude square? How do you compute the tree-level amplitude square from the squared amplituhedron? Right, those should look like a polynomial of x coordinates with only positive coefficient. But if you summing over all k sector and simplify to a local form, they're also relevant for the computation of energy correlator. This will be a direction that's still worth exploration. And then there's also the question I asked: how to recover how to go back to original correlahedron and in a way to compute all these things in a symmetric way. I mean, there's something we still don't know how to do. And finally, there's the question of what are all these F graphs evaluating into? I mean, what numbers and functions they evaluate into when you perform loop integrations. Okay, I'll just stop here and we can have more discussions.
Okay, thank you very much. Questions for Song? So maybe can I ask on the last thing of integration? So
yes.
Can you just repeat the setup was that it was on the Coulomb branch when the external were massive?
Yes. So this is what Simon and Frank did. That they use this. They view this F graphs as 10-dimensional things with not only the 4-dimensional distance but the extra 6-dimensional thing, which give you all the higher charge things. And if you take the limit that the 10D x1 square, x2 3 square, and so on goes to 0, all these integrals are still finite because you are not taking the 4D like limit. But they give you some Coulomb branch amplitude with, you can view them as some external masses, right? So this Coulomb branch amplitudes has an advantage that it's already, all the results are known. They're already given by integrability. But what I want to explore here are when you do it perturbatively, these integrals are very hard to evaluate. So there seems to be some room for computing these integrals and compare with the integrability result for this setup. Yeah.
But the loop momenta are still 4-dimensional.
Yes.
Yeah. Mm-hmm. Now these identities that you showed, they are probably very obscured if you think about cuts. Right, this combination has still non-trivial cuts, and you cannot a priori see why it's 0 at the level of cuts. Or can you say something?
Yeah, that I haven't thought about. I think, yeah. I mean, maybe you guys start with this simplest one. Why these 3 guys add up to 0 at
because the maximal cuts are all different. Yeah, it's different topologies. So.
Right. I think it involves a lot of, if you want to really prove it, like from integral point of view, there's a lot of IDP and so on. I don't think anyone knows how to do it. But from cuts, yeah.
Or it's not that the combination somehow parity odd integral, but it's 4 points, so it's not even clear.
No, not like that. I mean, it's a generalization of this kind of thing, but much more complicated. Now it's not among 2 integrals, but more integrals, even with their permutations, right? So, Yeah, I don't know how to see them from cuts. Yeah.
And also this drop of transcendentality. So normally for completely massless, it was always the case that there was some double pole in the cut structure, like for this 5-loop window diagram. So do you think this is the same here also?
Yes, yes. So for this guy, that if you weight 9, you can clearly see that when you cut down to some point, you see some double pole. Yeah, but the whole point is that this integral, when you combine them into Coulomb-Branch amplitude, they recover uniform transcendentality. So that seems to suggest that in this lie-like limit, there's a better way to organize them, like to combine them together so that you can have term by term UT integrals, right, which is no longer the case in our representation, or this DCI integral. Most of them are still fun, but starting 5 loops, some of them are no longer UT. So that suggests you should organize them in a different way, I guess.
Other questions? Now, in the completely massless case, if we just look at the 4-point amplitude, we know that the amplitude is one object, but if we, for example, care about IR, we would consider the logarithm of the amplitude because it exhibit the divergence. Now, because you are on the Coulomb branch, it's IR finite. Is there any reason to calculate logarithm of the Coulomb branch amplitude? Do you know?
Yeah. So I think Simon already in his paper with Frank, they already mentioned that if you there are different ways of taking the massless limit to go back to the massless case. I mean, the usual way, they give you a gamma cusp in the exponential, right? So in this way, because it's all given by determinant of ladder, so if you take it to massless, it's still an exponential thing, but now it looks like exponential of this gamma octagon. It's not a gamma cusp. So I mean, everything. If you start to remove the regulator, it still goes to something exponential. So you want to take the log, and this will be a way of perturbatively. I mean, very much in analog to what you guys did. Now, if you can take the log of these things at each loop order and remove the regulator, sending U and V to 0 or something, then you should see a perturbative calculation of the gamma octagon, not the gamma cusp in this way. Yeah.
Right. More questions? Comments? Okay, if not, let's thank Song again.
Thank you.